Hi, today we're creating a 6-dimensional Mandelbrot set using only a resource pack and a data pack. This is possible thanks to the experimental vanilla shader system, which allows resource packs to load custom GLSL shaders. I also made a companion web app with a few extra features. Like any standard Mandelbrot explorer, you can move along the complex plane and zoom in or out. Beyond that, you can also move along the Julia plane to explore different initial Z values. You can even rotate the viewport to face the Julia plane, which produces a Julia set. Inspired by the video from 2Swap, I added 2 axes to change the exponent. Along with controls to rotate the viewport towards the exponent plane. In total, that gives us 6 dimensions to explore. Before we begin, I'll briefly explain how the game's renderer works. Every model in the game is composed of vertices. First, the vertex shader projects these vertices onto the 2D screen. Then, a fragment shader applies colors to each pixel on the rendered surface. Finally, the post-processing pipeline re-renders the image onto a full-screen rectangle, allowing fragment shaders to apply effects to the entire screen. Since I want the Mandelbrot set to cover the entire screen, I'll override one of the post-processing shaders. A good option is the entity outline shader, which is activated whenever the player is looking at an entity with a glow effect. We can replace the fragment shader with a standard Mandelbrot function, then add colors by sampling a gradient based on the number of iterations it takes each point to escape. Now, let's make it interactive. To do this, we need to send data to the shader. Traditionally, this is done using uniforms, but we can't control those using commands. Instead, we have to encode the message by placing objects in front of the player and decode it in the shader by sampling the input image. Text displays can have their background colors be set to any arbitrary RGB value, making them perfect for transmitting a lot of data in a small area. We can encode the message into a text display's background color, then use a repeating teleport command to force the player to look directly at the entity. To read the message from inside the shader, we can simply sample the color at the center of the screen. In my first prototype, I managed the XY coordinates and zoom levels using a scoreboard, then encoded them in the red, green, and blue channels respectively. It did work, but with only 255 values per channel, the movement was very imprecise, especially after zooming in. So, I investigated other options. I realized the game supports persistent render targets, meaning we could generate an image using a shader in the current frame, and sample from that same image in the next frame, essentially allowing shaders to have memory. Instead of transmitting the full state to the shader, we'll just send the keyboard inputs and store all data inside an image. This approach has a few benefits. Firstly, we get much smoother animations since shaders run every frame instead of just 20 times per second. Secondly, we can write the bulk of the application in GLSL, which is much nicer to work with compared to Minecraft commands. Let's encode our keyboard inputs into the text display entity. Text display backgrounds are represented using a 32-bit integer divided into 4 8-bit channels: alpha, red, green, and blue. From my testing, the color isn't rendered exactly, so we'll use the first 3 bits in each color channel to pad for error. We'll use 6 bits to encode left, right, down, up, backward, and forward, which still leaves plenty of room to use later. To sample the entity, it needs to be fully opaque. We'll set the alpha channel to 255 by adding 255 left shift 24. The game uses signed integers, so this wraps around to a negative number. Finally, we'll add the error padding. I created a debug shader to help me visualize the message. At the top, you can see the input received by the shader, and at the bottom, the message being sent via commands. Now, the shader is able to receive messages, but for it to persist data, there are two problems we need to overcome. First, shaders are not like traditional programs in that we cannot write to a data buffer wherever we want. Instead, the program is instantiated for every pixel in the image, and each instance is only responsible for coloring one pixel. To work around this, we'll define data storages for each piece of data we need to persist. When writing to a specific storage, we'll check if the current pixel coordinate matches its assigned region in the image. If so, we'll output the color. Secondly, shaders use 4-dimensional vectors for colors, which are internally converted into 8-bit integers, whereas most of the data we want to store are floating point numbers. As luck would have it, 4 8-bit channels equals 32 bits, and floating point numbers are also 32 bits, so to store a number, we'll decompose it into its constituent bits and spread them across the 4 channels. Here's another debug shader I made to help me visualize the persistent state buffer. To make the movement less abrupt, we'll add a basic velocity system. Shaders run every frame. With our current implementation, the simulation would run faster on devices with a higher frame rate. I'd prefer the speed to be consistent, so we'll scale the simulation using delta time. There is one hurdle, however. Remember, each variable is updated by separate shader instances running in parallel. There is no guarantee that the last game time won't be overwritten before the other instances have had a chance to compute the delta time. To work around this, we'll write the results to a temporary swap buffer, then in a separate render pass, we'll use the built-in blitz shader to copy it back into the persistent buffer. Now, we'll generalize the Mandelbrot set to 6 dimensions. We'll replace the position and velocity with 6-dimensional vectors. Then, we'll replace the constants in the Mandelbrot function with the pixel's position along the 4 new axes. A lot of Mandelbrot visualizers use an escape radius of 2, but this is too small to support complex exponents. We'll increase it to the maximum value floating points can represent. Next, we'll implement special control items to select our movement axes. To do this, we'll associate each item with an integer ID and write it starting from this bit in the text display background. Minecraft doesn't have a left-shift operator, but we can simulate it using multiplication. Just as you can left-shift a decimal number by multiplying by powers of 10, you can left-shift a binary number by multiplying by powers of 2. In our case, we want to multiply the held item ID by 2 to the power of 19. Next, let's implement rotations. In 3 dimensions, it's common to think of rotations as occurring around axes, but rotations don't actually happen around axes, they occur within planes. This simplification only works because in 3 dimensions, there is only one axis orthogonal to any given plane. In 6 dimensions, there are 15 distinct rotation planes. We can generate a rotation matrix for any cardinal plane using this function. To apply the rotation, we'll simply multiply the direction vectors by the rotation matrix. I wanted to rotate the Mandelbrot set into a Julia set. To figure out which planes to rotate within, we can focus on the left and up vectors. In the Mandelbrot set, they are the x and y axes, whereas in a Julia set, they are the z and w axes. To put this a different way, we want to rotate x onto z and y onto w. So we should rotate within the xz plane and the yw plane simultaneously. We'll apply the same principle to rotate from the Mandelbrot plane towards the exponent plane, or from the Julia plane towards the exponent plane. Finally, we'll add 2 more text displays facing away from the player in case they accidentally switch to third-person mode. During development, I found many interesting shapes and was frustrated that I couldn't find my way back to them. so I created a web version specifically to save and restore my position.